Hi, welcome back to es346 Basic Thermodynamics. This is module 3.6, Non-Ideal Gas Equations. The section in the textbook is section 3.8. Here are the two learning outcomes for this module. At the end, you will understand the basis for the van der Waals equation of state constants, and you will be able to calculate the accuracy of a non-ideal gas equation of state. So the equation of state, the first one I want to talk about is van der Waals equation of state, and it's shown here where we've got P, V, and T, three intensive variables, but then there's some extra parameters. There's this parameter here, A over V squared, and then this minus V. Recall the ideal gas equation, which says that PV equals RT, and you see a similarity between that. And if we go back to the compressibility equation, which was PV is equal to ZRT. We could think of the ideal gas equation as a zero parameter equation of state. There's no adjustable parameters. The compressibility as a one parameter equation of state, where Z is an adjustable parameter. And now we're looking at a two parameter equation of state, where we've got this value A and this value B. Now, values of A and B are a little different than compressibility. They're actually constants that are particular for the gas. And so in order to calculate those, what we do is we rearrange this equation in terms of P. So we can solve for P, and that would be equal to RT V minus B minus A over V squared. So I've just done some rearrangement. Now to help visualize this, I show a PV diagram with the saturation curve, and shown in green is an isotherm. So recall an isotherm at a lower temperature might look like that. The one shown here is called the critical isotherm because it goes through the critical point. And right there is an inflection point that goes through. Now recall from calculus, if you have an inflection point, the first derivative, or in this case the PdV, would be equal to 0. And likewise, the second derivative, d squared p dv squared, is equal to 0. Now we have an equation for p as a function of v, so you could go ahead and do this calculus, do this first derivative, second derivative, set the resulting equations to 0, and solve simultaneously for the parameters a and b. Now it's a lot of algebra, and I don't expect that you have to do that, but I show here what the resulting values are, the value for a and the value for b. It's a function of the value r and then t critical and p critical, because we were using the critical point to evaluate these parameters. Now the physical meaning of this first parameter, the A, is accounting for intermolecular forces. Molecules that are alike tend to be attracted to each other, and so we make an adjustment to the pressure, we can account for that. The second one is the parameter B, and that's accounting for the finite volume of the molecules in the space. Now here I show another equation of state called the Beatty-Bridgman, and it looks again sort of similar, but we've got a lot of parameters and we have a couple extra ones. Here we have a parameter A, B, and C. Furthermore, it turns out that those are even longer functions as well, so we need to plug this in for A and then plug this in for B. So you see there's a lot of parameters. This is a 1, 2, 3, 4, 5 parameter equation of state. But these more parameters we have, the better they tend to fit the actual behavior of the phase diagram. Now, to get those values, they tend to be tabulated, and here I show table 3.4 from the textbook that has parameters for Beatty-Bridgman of these 5 parameters. So for a given gas, you would go and look up those parameters and plug them in here, and then what you're going to be left with is simply P, V, and T. So any two of those and you can solve for the third. So it's very similar to the ideal gas equation. We just have this extra step we need to go through. Now this is pretty complicated to do when you do it by hand, but computers do this really well, or putting them into a spreadsheet. And that tends to be what these equations of state are used for. So let's go ahead and do an example. And what we want to do is calculate the air in the specific volume when using the ideal gas law. And what we're given is water at a pressure and temperature, pressure of 5 megapascals and 300 degrees Celsius. And we can determine the air from the ideal gas law because we can use the tables to find the actual value. The tables are the true measured value. So if we go to the tables, and in this case we'll use table A6, we're going to go ahead and look up what the volume is. And the actual volume is 0.04535 meters cubed per kilogram. So we got that from the table. But now let's use the ideal gas equation, solve for V, and find out how far off it is. So rearranging the ideal gas equation, V is equal to RT over P. I look up the value of R on table A1, and that is 0.4615. My value of T is 300 plus 273. To convert it into absolute, anytime you use the ideal gas law, they need to be absolute temperature divided by the pressure of 5,000 kilopascals. And that volume is equal to 0.0529 meters cubed per kilogram. So let's calculate what the actual air of that is. So what we'll do is we'll take the difference between the actual value, 0.04535, subtract the ideal gas equation value, 0.0529, and then let's normalize it by the actual value, 0.04535. And that is 0.17, which means that our error is 17%. Not an insignificant amount of air using the ideal gas equation. Alright, now let's use van der Waals equation of state, two-parameter equation of state, calculate the air and find out if we can do any better. So when we're using the van der Waals equation of state, the first thing we need to do is determine those parameters A and B. So here I'll get A, I'll look at my value of R, T critical and P critical for water, and find out that numeric value. It's 1.71. And then I'm going to go ahead and calculate my value of V. Again, using the critical properties of water, that's 0.0017. And now I'm going to go ahead and plug those in and solve for V. So I'm going to rearrange van der Waals equation to be equal to V is RT over P plus A over V squared plus V. Although I kind of run into a problem here. I'm trying to solve for V, but V appears on the right-hand side as well. And in fact, no amount of rearrangement can I isolate V on one side of the equation. So therefore, in order to solve this problem, I'm going to guess a value of V and put it in on the right-hand side, solve for a new value of V, and continue to iterate until I condense down onto a single value. If you go ahead and do that, it only takes a couple times. I find out that the volume is 0.0477 meters cubed per kilogram. So now let's go ahead and calculate the air using van der Waals. So we have the actual value, 0.04535 minus 0.0477, normalized by the actual value, and that is 0.052 or 5.2% air. So a much, much lower amount of air. It's still not perfect, but we got a lot closer.